Okay, here we're going to solve another of the classic optimization problems. For this problem, we're trying to find the maximum area of this rectangle we can, but it's got to be bounded within this semicircle given by this equation y equals the square root of 25 minus x squared. So that would be half of a circle of radius 5. And so, you see there are different options here. You could have a tall, skinny rectangle that would touch this curve, but it wouldn't have very much area. Or you could have a kind of wide, short rectangle that would not have a lot of area. Or the optimal solution is probably the most likely somewhere in the middle, but we don't know exactly where that is, and it's kind of difficult just to see based off of a graph and whatnot. So we're going to start this by writing our objective function, which is what we're trying to optimize. In this case, the area. We're trying to find the maximum area that we can. So we're going to write the area of this rectangle. Now, what is the area of the rectangle dependent on? Well, it's length and its height. And that can be judged by whatever xy point this is at. So we call this xy, right, because this is the x coordinate and this is the y coordinate of that point. Then the area would be not x times y, but you see the actual length of the base of this rectangle is actually 2x. So we'll say 2x times y. Now the problem with this particular optimization problem, as well as every other optimization problem, if you've seen my other two examples, we've seen the same issue crop up. This guy that we're trying to maximize, or we're familiar with how to maximize functions just from relative extrema and whatnot, which is what chapter this optimization section falls in. You would want to take your function, take its derivative and set it equal to 0 to find the critical points which lead to the relative maxes and mins. But this assumes that there's only one independent variable, right? Because it's a two-dimensional graph. A should depend on one variable. But here A is dependent on not just x, but x and y. So what you have to do for this problem, as well as every other optimization problem, is use the constraint, which we need to identify, to eliminate one of these variables. Now, what is our constraint? Well, the constraint is obvious. The rectangle has to be bounded underneath that semicircle. So we know that for any xy point that we chose along the edge of the semicircle, it has to be held to the fact that y equals the square root of 25 minus whatever x is squared. So we can use that to our advantage. And so if this was a different problem, you'd use the different constraint. But since y is equal to root 25 minus x squared, we can take the y out and substitute this in its place. So I went ahead and written a here. Now we have to take its derivative, and this is great because a is just a function of x. So this will be the product rule since we have two expressions multiplied times each other. We have the derivative of the first times the second plus the first times the derivative of the second. Now the derivative of the second is going to require the chain rule, so you might want to do this one on your scratch paper or what have you. But the final result after you differentiate this would be negative x over the square root of 25 minus x squared. Now I did skip a few steps there, so you might want to go slowly through this and look at how to differentiate that. We'll set this equal to 0, and then we'll solve this. So first thing we'll do is we'll take this negative expression and add it to the right hand side. So we have 2 square root 25 minus x squared equals 2x squared over square root of 25 minus x squared. And then we'll take this radical and multiply it to the left hand side to get it out of that denominator. Now what's going to happen is you'll have square root of 25 minus x squared times itself. This is the same expression. So if you have a square root that's squared, the square and the square root negate each other, and you just get 25 minus x squared only equals 2x squared. So distribute the 2, you get 50 minus 2x squared equals 2x squared, and then you get 50 equals 4x squared when you add the minus 2x squared to the other side. And solving this for x, you would get technically plus or minus the square root of 50 over 4, but technically we don't have to write the plus or minus simply because you wouldn't be considering negative x values as far as the width of your rectangle goes. So this would be x equals, the square root of 50 is 5 root 2, because that's 25 times 2, and square root of 4 is 2. So this would be your x coordinate that would give you the optimal area under the curve. Now after this, you have to go back and find the equivalent y value. Now we're going to use the constraint to do this, because if you know the x, then the y will follow. And it turns out if you plug in 5 root 2 over 2 in for x, then the y value turns out to be 5 root 2 over 2 as well. So here's your x, y coordinate for the optimal solution. Now, if you're concerned that that might give you a minimum solution, because we never really specified based off of this critical point if it was a max or a min, I'm not going to do it in this video, but what you could easily do is go and take this 5 root 2 over 2 number and try a sample point or a test point before and after 5 root 2 over 2 and plug that into the derivative function for a and determine that a itself is increasing before 5 root 2 over 2 and decreasing after 5 root 2 over 2, because the derivative before 5 root 2 over 2 would be positive and afterwards would be negative. So I'm not going to take the time to go through and do that algebra, but these would be the dimensions of the rectangle that gives you the maximum area. Now we also want to make sure that we answer the question that was actually asked for. Now these would certainly give you the dimensions of the rectangle of maximum area, or they would lead to it, but two things we need to clarify. Even if we were wanting the dimensions weren't that x coordinate, it would be twice that x coordinate. But it turns out if we read this question, what was actually asked for was not the dimensions at all. It was what was the maximum area that this rectangle could attain. We want to be real careful that we give the appropriate answer. So the actual area would be 2x times y. So we have 2x times y, where the x and the y are both 5 root 2 over 2. 5 root 2 over 2. All right, a little bit of algebra. One of these factors of 2 cancel. Root 2 over 2 times root 2 over 2 is 2, and so they would cancel with this 2 in the denominator, and so your final answer would be 5 times 5, which is 25 units of area, whatever the given units are. If we were asked for the dimensions of the rectangle, it would be 5 root 2 over 2 for the height of the rectangle, but it would be twice that for the width, because remember it was 2x wide but only y units tall. So if you doubled this, you would just get 5 root 2. So the dimensions of the rectangle and the maximum area that you would get from that particular rectangle. So we just want to make sure that we answer the appropriate question.